All right, the next lesson in geometry is called density in design problems. Okay. So when modeling in 3 dimensions, you are often interested in maximizing or minimizing some aspect of the situation. Perhaps you want to minimize materials used in order to minimize cost. Perhaps you want to maximize the volume in order to maximize profit. When working with these types of problems, you are going to first create your model. Then you're going to test different possibilities or create an equation that shows the relationship between the variables you are looking to maximize and minimize and another variable in the problem. Often we will use the following formulas. So this is the formula we're going to use for the first 2 examples. Density equals mass divided by volume. Okay. So example 1. If 325.7 grams of gold has a volume of 20 centimeters cubed, what is the approximate density of the gold? Okay. So let's start by copying our formula above. Density equals mass divided by volume. Okay. Okay, and let's substitute. The mass is 325 grams. $325.7 grams. The volume is 20 centimeters cubed. And you can divide those. 325.7 divided by 20. It doesn't tell you where to round, so I'm just going to say density equals. I'm going to say 16.285. The units are going to be grams divided by centimeters cubed. Okay, so that's example 1. That was an easy one. Let's look at example 2. If the approximate density of a diamond is 2.7 grams per centimeter cubed, what would be the approximate mass of a diamond whose volume is 3 centimeters cubed? Okay, so you're trying to find the mass. Okay, let's look at the equation above. If you want to solve for the mass, meaning you have to get the mass by itself, you're going to multiply each side by volume. So mass is going to equal density times volume. That's our formula. Mass equals density times volume. So mass is going to equal a density is 2.7 grams per centimeter cubed times 3 centimeters cubed. Okay, so what happens is you're going to multiply the numbers. 2.7 times 3 is 8.1. As far as the units go, these centimeters cubed and those centimeters cubed divide out, and the units you're left with are just 8.1 grams. So that's the answer. Okay. Example 3. A water company inherits an L-shaped water tower as shown below. The tower is 10 feet thick throughout the entire tower. 1 cubic foot of water equals 7.48 gallons. How many gallons of water can be stored in the water tower? Okay. So what I'm going to do is I'm going to break this apart into 2 shapes that I can easily get the volume of. So let's break it up over here. So off to the side, I'm just going to redraw these shapes. Okay, the shape of the top is going to be 18 feet. And this part is the same as this part. This entire side is 40. This is 25, so this part's going to be 15. 40 minus 25 is 15. And the bottom part, of course, is 25 by 30. For consistency, I'll just redraw that down here. "25 feet by 30 feet. Now you're saying volume, I only see 2 dimensions. Remember, it says in the problem, it's 10 feet thick throughout the entire tower. Okay, so let's start. Let's get the volume of each part. Okay, let's start with the small section, base times height. So 18 by 15 by 10. "18 times 15 times 10 gives you 2,700. Feet cubed. The volume of the other part is going to be 25 by 30 by 10. "25 times 30 times 10 is 7,500. So let's get the total volume. You're going to add those together. Okay, so that's our next step. 2,700 plus 7,500. It's going to give you 10,200. But now you're going to have to convert that. Okay. The question is, how many gallons of water can you store in the water tower? Each cubic foot contains 7.48 gallons. So now we're going to have to convert. I start with this unit, 10,200 feet cubed. And I do my conversion over here. Whatever these units are, they're going to go down in the bottom. And I want to convert that to gallons, so that goes up top. The conversion rate, according to the problem, is 7.48 gallons for every 1 cubic foot. So 7.48 gallons per 1 cubic foot. And the idea is if the number's up top, you multiply. If it's in the bottom, you divide. I don't have to divide by 1. That's meaningless. So I'm going to do 10,200 times, because it's in the numerator, times 7.48. I get the answer of 76,296 gallons. Okay. Let's say the water tower can store 76,296 gallons of water. Okay. That was a tough problem because you had to work with a composite figure, and then you had to convert at the end. Example 4. The density of steel is about 0.28 pounds per inch cubed. Could you lift a solid steel ball with a radius of 3 inches? And could you lift a solid steel ball with a radius of 7 inches? Okay, so let's start by finding the volume of each ball, and then we're going to convert to pounds. Let's start with the 3-inch radius. Here's the formula for the volume of a sphere. It's a solid steel ball, so it's a sphere. The first ball has a radius of 3, so let's substitute 3 for the radius. 4/3 times pi times 3 cubed. 3 times 3 times 3 is 27 times 4 divided by 3 times pi. Well, let's first put it in terms of pi. You're going to get 36 pi. And then 36 times pi. Let's put out all the decimals for now. 113.0973355. It's cubed. Now what you're going to do is you're going to convert that to pounds. Okay? So let's do a conversion. We start with these, because this is the volume. We start with that. 113.0973355 inches cubed. And we're going to convert 0.28 pounds per 1 inch cubed. If it's in the top, you multiply. If it's in the bottom, you divide. So I'm going to do 113.0973355 times 0.28. And it's going to give me approximately, I'll say 31.7 pounds. LBS is pounds. So now the question is, could you lift that? So I'm going to say, yes, I could lift 31.7 pounds. All right, now let's do the same thing for the other part, because it's the same thing but with the 7-inch radius. So let's calculate the volume of that, then we'll convert it to pounds. So again, it's a solid steel ball, so I'm going to say volume equals 4/3 times pi times radius cubed. That's the volume of a sphere. And this time the radius is 7 according to the problem, so 4/3 times pi times 7 cubed. $457.33333 pi. Multiply that out. Approximately 1436. 0.75504. That's the volume. And now you're going to convert that volume into pounds. And you're going to see, can you lift it or not? So you take that volume. And we're going to convert. According to the problem, 0.28 pounds is 1 inch cubed. So that's what you're going to multiply. You're going to do this number, 1436.75504 times 0.28. That's going to give you 402.3 pounds approximately. So just answer the question, yes or no, could you lift that? I think everybody's going to say no. No, I could not lift 402.3 pounds. All right, so that's that problem. Okay. All right, one more problem. Example 5. An air conditioner is being purchased for the room below. According to the U.S. Department of Energy, to determine the cooling requirement of a room, use 2.5 BTUs per cubic foot of airspace. To this value, add an additional 1,000 for each window in the room. This room has 4 windows. Determine the number of BTUs needed to cool the room. Okay, so what you're going to have to do first is we're going to have to find the volume. It's a composite figure. Find the volume of each shape and then add that together. And then we're going to convert that to BTUs. Okay, so let's get the volume first. Let's start with the easy part, which is the rectangular prism. Okay, so rectangular prism, I'll write down. Volume equals base times height. The base is a rectangle, so 24 by 18. And then times the height of 9. Okay? 24 by 18, and then times the height of 9. That's going to give you 3,888. Okay, so that's the rectangular prism. Now let's do the triangular prism. Okay? So the triangular prism. Again, volume equals base times height. Okay, the base is a triangle. So you're going to use the formula for the area of a triangle, which is 1/2 base times height. Okay, so if you try to picture this triangle, the base, now let me color it in. Oh, let's get some colored pencils out, I guess. Why not? It'd be hard to see. That blue is the base. And the height would be this, in orange. Okay? So the base is going to be the blue. And that blue, hopefully you can notice this, that blue is the same as this length right here, which is 18. Okay? And the height in orange, hopefully you can notice this, but that's this number right here, that's the 6. So that's actually not that bad. Okay, so 1/2 times 18 times 6, that's the triangular base. And then the height of that prism is 24. So those are the 4 numbers you're going to multiply. 1/2 times 18 times 6 times 24. That gives you 1,296 feet cubed. Okay, so we just got the area of each prism. To get the area of the entire room, you're going to add those 2 numbers together. So let's do that next. Okay, volume, to get the volume of the total room. Okay, total volume equals 3,888 plus 1,296. Add those 2 numbers together. 5,184. Now what we're going to do is we're going to convert that into BTUs, because it's part of the problem. Okay, so we're going to convert 5,184 feet cubed, convert that into BTUs. It says in the problem, 2.5 BTUs per every cubic foot. So 2.5 BTUs per 1 cubic foot. Like I've been saying, if the number's up top, you're going to multiply. So 5,184 times 2.5 equals 12,960 BTUs. Okay, so now what we're going to do is we're going to take that number and it says we have to add on 1,000 BTUs for each window. And this room has 4 windows, so it means we're going to add on 4,000 BTUs. To get the final answer of 16,960 BTUs. Let's say this room will need 16,960 BTUs to be cooled properly. And there you go. That's the end of that lesson. That was called Density and Design Problems.